In this video, we'll look at how we can train a convolutional neural network, CNN, to classify the CIFRAR dataset. And so let's create a cell up here. We are going to use a convolutional neural network, CNN, and we are going to work with the CIFRAR10 dataset. And this example is directly from the docs, and I'm copy pasting the code that's in the doc inside of the Google Colab. It's just that I'm talking through the code as we go through this video. And the CIFRAR10 dataset consists of the 60,000 images. Each image is 32 by 32 pixels, and there are these classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and the truck. And that's the dataset we'll be able to import directly into the Google Colab notebook using the TensorFlow datasets. So let's go ahead and first import the libraries that we need. We need import TensorFlow as TF, and next we need to import Keras. So from TensorFlow.keras import datasets, then we import layers and models. So there's 3 items there, and after that we can import the matplotlib. Import matplotlib.pyplot as plt, and that's because we'll be doing some plotting. And wondering why we have this squiggly line here. Let's run this and see if we get an error. So that seems to be okay. Now we'll download the CIFRAR10 dataset. So let's create another heading: download CIFRAR10 dataset. And for this, we'll directly get the values for train and test split ready-made. So we'll put them in respective variables: train underscore image and then train underscore labels. So that's a train set. And for test, we have test underscore image. Let's put an S there. So images and test underscore labels. And after this, we can use the datasets dot CIFRAR10 dot load underscore data, and with this then we should be able to import the dataset inside of the notebook, and like so. Okay, and we can look at train underscore images dot shape, and we see that we have 50,000 images that are 32 by 32 and pixels, height and width, and there's it has 3 channels: RGB, so red, green and blue. Again, for test, as we should see here, we have 10,000, so total 60,000 as we saw in this case. Okay, the next thing we need to do is normalize the pixel values. Normalize the pixel values to a range 0 to 1. And right now, if we look at train underscore images, we see that the values are up to 255. So they'll be up to 255 and 0 to 255, and therefore we are going to normalize it by dividing by 255. So train underscore images and then test underscore images is equal to train underscore images divided by 255.0, and test underscore images divided by 255.0. And this way now we have normalized the data set, and as you can see, these are all now float values that are between 0 and 1. Next, we'll take a look at how the images look like, and so we're going to visualize the images, and that is to say we can verify if the labels and the images do match. And for class names, then these are the labels. One is airplane, so these are the same labels that we saw earlier: airplane, automobile, bird, cat, deer, and then we have the dog, frog, then we have horse, and we have ship and truck, and lastly the truck. So these are the class names we have, and we can type these out below each of the images that we'll be plotting now. And so for plotting, we have plt.figure, fig size is equal to 10 by 10. We'll provide a tuple here, and then inside of the for loop we'll create the subplot. So for I in range 25, and we'll have 5 by 5 columns, 5 rows, and so total 25 images will be plotting. plt.subplot, and we have 5 rows, 5 columns, and we'll put the first plot at location I plus 1, so it will be 1, location 1, and plt.x ticks. So here we do not need any information there, so we are simply going to create blanks there by specifying empty square brackets, and we'll set the plt.grid to false. Okay, so with this, then we can now look at the image. plt.imshow train underscore images, and we can put square brackets I, so we are fetching that particular image at that index in the array, and image is itself an array that is stored. If we look at train images, if you look at the type train images, here we have this as numpy array. If you look at train, we already look at the shape of it, train images dot shape, and as you can see, it's an array with which has these images as arrays. And so if we were to pull an image, this is the way we could pull on the image. And here we have what, let's look at the shape of this. Yep, so that's the 32 by 32 by 3. And if we were to plot this, plt.imshow, and we remove that, and then look at this, we see that that's a frog image that we have plotted. So on similar lines, what we are doing up here is we are plotting those images, and we have plt.xlabel class underscore names and train underscore labels, and then square bracket I, square bracket 0, and that's again because the train underscore labels, if you look at the shape of that, we have labels, ELS, made a typo there. We see that it's 50,000 by 1, and so if we look at the array itself, we see that it has 2 dimensions, and if we specify 0, we get this value array, and if you want to fetch the value at index 0, we need another 0, and that's why we have this second 0 right there. Okay, so with this, then once we have that all set up, we can now go ahead and plot this array. So I'm wondering why we have this line. Let's see, we'll plot plt.show, and oh, that's the typo again, BELS. And we should now see a set of 25 images from CIFRAR10 dataset as we have here, and our labels: frog, truck, deer, etc., etc. So it looks like the dataset is looking good inside of the Colab notebook. We can now go ahead and create our model. So create the convolutional base, and in this we are going to use the conv2d and max pooling 2d layers. Okay, and for this, then we'll create the model. Model is equal to models dot sequential, and this is another way we can create layers by using model.add. In the previous video we used a different method. Model.add layers.conv convolutional 2d, and here we have 32, which is the filters, number of filters. Then we have the kernel size, that is 3 by 3. Activation is equal to ReLU and ReLU, and then we have the input shape. The input shape again is the images that we have, and they are 32 pixels by 32 pixels, and we have the 3 channels in there. Next, we need to you add a max pooling 2D. So add layers dot max pooling 2D, and again in this we specify the dimensions 2 by 2, and so that's this layer, and we'll repeat this. I'm going to copy these sets of lines, and again we have layers.conv2d, and we have 64 as the number of filters. Then we keep the kernel size the same. Activation also is ReLU, and we do not need this right here, which is the input shape, because that's going to be the output shape of the previous layer. And then we have the max pooling 2D, again the same. Finally, we will add another conv2d layer on top of this right here, and what we'll specify here is the same that we had earlier. 64 filters, 3 by 3 is the kernel size, activation is ReLU, and we can look at the TensorFlow. So TensorFlow or Keras conv2d, and if we look at the syntax or in the help menu, we see that this is the number of filters, we have the kernel size, and the strides is of size 1 by 1. Right, so now we can run this cell, and we've now created the model. We can look at the model summary by typing model.summary open close parenthesis, and here we see that this is the model that we have created. And point to note is, as we step deeper into the network, we see that the dimensions of height and width are diminishing, and the depth is increasing. Next, what we can do is we can add dense layers right below this one. So let's do that. So add dense layers, and for this we will proceed with the same model.add and layers.flatten. So what we are trying to do here is we are going to flatten this out, and then pass that into a dense layer. Model.add layers.dense 64, and activation will again use the ReLU activation. And finally model.add layers.dense, and in this case we have 10 in here because we have 10 different classes inside of this dataset. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's the CIFRAR10 dataset. And again, we can look at the model summary, and we should see the additional layers that we created just now. So these layers. So if we look at this 4 times 4 times 64, that should give us 1024, and that's what we have here after flattening it. And then we have these 2 dense layers on top of this, with a final layer with 10 values as the output. Next, once we have the model created, we are now good to compile this. And to do that, let's create a heading here: compile and train the model. And you may have probably noticed by now that using Keras API, it becomes really easy to train a convolutional neural network by just writing these few lines of code. For compiling, we would type model.compile optimizer is equal to Adam. So we'll use the Adam optimizer. Loss is equal to tf.keras.losses.sparse categorical cross entropy with a capital S, C, and another capital C for cross entropy, and inside of parenthesis from underscore logits is equal to true. And then we have the matrix, which is accuracy. Okay, so that's the model. So we run this and we have compiled the model. Now we can fit it. So history is equal to model.fit train underscore images, train underscore labels, epochs. Let's set the epochs to 10. And then we have validation underscore data is equal to date. For validation, we can specify the test images and test labels. Okay. And so when we run this, this is going to take a while to run. So what I'll do is I'll stop the video here and come back when this run is finished, and then we can continue on to plotting the results. Welcome back. The run is now complete, and here we can see that the validation accuracy is 70%, and the training accuracy is 78%. And as you can see, the loss has decreased quite a bit. From the beginning it was 1.5, it dropped down to 0.5. Finally, let's look at how we can plot the accuracy of the model. ELT.plot history history, and we can use the accuracy. Label is equal to accuracy, and then we can plot plt.plot history. Again, we have the validation accuracy, and the label again is going to be validation accuracy. And we'll add labels. X label is epochs, and then we have Y label is accuracy, and we have plt.ylim. We'll go from 0.5 to 1, and we'll add legend plt.legend and legend, and here the legend will add the position where we want this to appear, lower right, and finally test underscore loss comma test underscore accuracy is equal to model dot evaluate test underscore images test underscore labels verbose is equal to true 2, and now we should be able to see the plot for the accuracy of validation for the validation set and the train set. As we can see, the validation set does catch up, but it levels up at 0.7, around 0.7, and if you look at the test accuracy, it is 0.70, and it's similar to what we had for the validation score, 0.70. So that was it for this video. I hope in this video you learned how to train a convolutional neural network to classify images. We'll continue this series and we'll look at some other implementations in TensorFlow in Keras. Until then, please like, share and subscribe. Thank you.